The reactions we have discussed so far were well-mixed, uniform concentration systems. Now we are going to switch to the reactions with an interface. What are those reactions? Those reactions may have interfaces across the gas-liquid boundaries, across the liquid-liquid boundaries, across the gas-solid or liquid-solid, in other words, fluid-solid boundaries. So when a boundary exists, that boundary imposes its own limitation on how fast molecules migrate through that boundary. And we are going to today discuss how that boundary influences how fast we can conduct our reaction. So let's start with our former examples of a perfectly mixed continuously stirred tank reactor, where our fluids entered and left, and everything was uniform, including temperature and the concentrations of all the species. The other extreme of this reactor was the plug flow reactor, where we had a fluid package traversing through the reactor without interacting with the fluid package neither before nor after itself. That was a closed system, imaginary closed system, and that imaginary closed system we started to represent as our ping pong ball that is well mixed but with closed boundaries. So we had idealizations in all three cases. Here we had steady flow in and steady flow out, uniform concentration throughout. Here we had no flow in or out, but uniform concentration throughout. Here we had steady flow in, steady flow out, but the fluid package did not interact with the fluid behind nor the fluid in front of it. Or in other words, it was a closed chamber similar to the batch reactor. Now we are going to extend our discussion and extend our problem to more realistic situations. Situation number one is the packed bed reactor. Packed bed reactor is a reactor where we have, in most situations, solid packings. So now I have drawn for you perfect spheres. They don't have to be the perfect spheres, but for the sake of our initial discussion, we will start with the perfect spheres. The fluid is going to flow through these perfect spheres, will distribute itself, and will leave the system after the needed chemical conversion has taken place. Now, we might imagine those perfect spheres as catalysts, or we might imagine those perfect spheres as solid ores, for example, oxides that need to be reduced with the flow of oxygen, reduced with the flow of hydrogen or carbon monoxide. Now, let us have a close-up view of those spheres, a little bit enlarged, and let us imagine our fluid approaching to this perfect sphere. The sphere is stagnant, and the fluid, because of its momentum, will go over and beyond that sphere. So this is going to be, the lines that I'm drawing are the streamlines of the fluid that is traversing across this sphere. Now let's have a little bit more close-up of that sphere. So I'm going to enlarge the sphere, and I'm going to look at only this portion of the sphere. So this is my portion that I have chosen to look at. This part is my solid. I have a boundary layer. So this is the boundary layer. And this boundary layer is due to the stagnant portion of the fluid flowing across it. Okay? We have a non-slip boundary condition on the surface of the sphere. Because the solid is stationary, the fluid that is close to that solid is also stationary. Until when? Until we are through the boundary, which is going to the molecules after the boundary are going to sense the momentum of the boundary of the molecules in the next boundary. Right, so here we have a stagnant boundary, we have fluid flowing through it, and of course you can imagine that this fluid flowing at infinitely far away from the solid boundary is going to have a velocity which we call v infinity, that it is far, far, far away from our boundary, right? And at the solid boundary, our fluid is stagnant. And if the velocity here has a finite value, if the velocity here is 0, we should anticipate and be able to determine a velocity profile, that the velocity of the fluid is changing with respect to the position that is indicated moving away from the surface. So now let's have a little bit more close-up view. I'm going to take this portion. When I take this portion is nearly flat. I don't have to draw an arc nor a sphere. It's a flat. And now I'm drawing a vertical flat line. Right? This is my solid now. You can see as I'm moving closer and closer to the small molecular level where I have to investigate to understand how the chemical reactions are proceeding, my dimensions change shape. My surfaces change shape. My dimensions get smaller, my surfaces change shape. Now let's reflect this velocity profile onto this structure. So here I have an imaginary boundary. There is no boundary here. Remember, I'm expanding this particle. I'm getting closer and closer to this particle. So there is no physical boundary as far as fluid is concerned, except the solid-fluid interface. Here, my velocity, let's try to regenerate, yes. Here, my velocity is v infinity, and this distance is, with respect to the fluid motion, infinitely far away. Here at this boundary, my fluid velocity is 0. And this domain has a velocity profile like this. My dimension and my velocities are increasing towards bottom. So let's call our coordinate system as this is x and this is z. All right? So we have a velocity profile. Now, because we have a velocity profile, we now understand that the axial movement of the fluid molecules have different velocities at different x values. This is one condition to keep in mind. But remember, we are going to generate a model to understand how the reactions take place on the solid surface at the solid fluid interface. Now, I hope that you are already at the conclusion that if there is a velocity profile, there should be a concentration profile. Now let's discuss that. Now if this is V infinity, right, it's the bulk fluid, bulk of the fluid, here this is V infinity, and let me fill the gaps of my exaggeration. I have another sphere here, another sphere here, another sphere here, and so on and so forth. So the open channels that fluid can flow does not change much with axial position in our packed bed model. So we can comfortably assume that this V infinity is constant throughout this reactor, that the fluid is not flowing fast at certain portions and slow at certain other portions. In reality, this might happen, but for the sake of discussion and for the sake of deriving the details of this equation, we're going to take that the bulk fluid motion, bulk fluid velocity is going to remain uniform throughout our reactor. As a result, here we have a C infinity of our solute. Bulk motion, bulk velocity, and bulk chemical composition, C infinity. And also we are going to have C0, all right, at the boundary. Suppose that we have the task of reducing an ore. Like, for example, we are given an iron oxide ore, and we are given the task that we are going to reduce this ore to its metallic state. This is the reaction that is going to take place. Now this reaction, here I'm flowing hydrogen through this system, and this reaction is going to take some time. I'm focusing my attention on one sphere, and this is the reaction that is going to take place on that sphere. Hydrogen is flowing. C infinity is dictated by the gas law, the pressure, temperature, but also we know that as we move along the reactor, our gas will start having some water vapor and will lose some of its hydrogen due to the reaction. So the concentration will change as we move along the length of the reactor, but this is not the length of the reactor. This is this small incremental dimension on our sphere. So when I plot the concentration as a function of position of the, let me call this gas side. Here I have the interface, on this side I have solid, on that side I have gas, and this dotted line indicates the boundary between the bulk fluid and the boundary layer. So if I just take the position of x0 here, here Ca is Ca bulk, and at the moment it arrives on the surface, it reacts immediately. Because it reacts immediately, its concentration is 0. So we have some sort of a profile, concentration profile. We don't know the shape of this concentration profile, and we are curious. What is the shape of that concentration profile? The shape of this concentration profile depends on how this transport of species A take place across this boundary layer. If we have a simple molecular diffusion in the gas phase, we have a straightforward film mass transfer process where the rate of this film mass transfer process is equal to K times delta C. K is the film mass transfer coefficient, delta C is the concentration gradient, but I have to be careful and I have to take the area across which this transport is taking place into concentration. So we have defined, I should write K times A to be loyal to the convention, C infinity minus C surface. So when I write this rate as such, my concentration is going to have a flat profile. How did I arrive here? I arrived here from what we call as two-film theory. In that theory, we assume constant molar flux of species. In other words, we assume that if we say that this is our molar flux minus d times dc over dx, as x increases, c decreases, and we have to have a constant positive flux, therefore negative. This is constant. So with the constant molar flux, we start from the Fick's first law, and the derivation of solution of that ordinary differential equation leads us to the conclusion that the mass transfer coefficient is equal to the molecular diffusivity of the species that are interest to us divided by the distance delta. So, so far, we know how to evaluate this mass transfer coefficient. This interfacial area is the biggest problem of all the chemical engineering problems, that we have no way of measuring that A directly, and that A, depending upon the types of the reactors, may not be constant. But let's leave that discussion to our fluid-fluid contact reactors. So here now we have our mass transfer coefficient at our disposal. We know the gas phase concentration profile. Now the question is how the solid will behave. Now let's, this time we zoom out and shrink our perspective. Let's look at the solid side. On the solid side, you can imagine that we will have a moving boundary, that the surface of the solid will be reduced. This is going to go deeper and deeper into the bulk, or we're going to have a core that is shrinking. A core that is shrinking. So the periphery of the core is reduced, but the core itself is oxide. So as a function of time, our core is going to shrink, and eventually it will disappear. This is what I discussed here, is the shrinking core model. What I want you to pay attention is the term model. We will discuss this shrinking core problem more in depth later, but for this discussion, pay attention to the word model. This indicates that what we are doing here is generating a workable model that will allow us to generate a mathematical relationship with which we will be able to estimate the behavior of the system. Okay? So, this wraps up the packed bed discussion of the reactions with an interface. Now let's move on to another domain. Let's have a CSTR or mixed flow reactor. Let's have a mixed flow reactor. Let's have a mixed flow reactor. I refrain using the term CSTR because that is the idealized situation which is reflected on the upper side of the board. This mixed flow reactor contains all sorts of non-idealities that we have to deal with. In our mixed flow reactor, you're going to have a liquid phase coming in. We have an impeller. Now we are used to this type of configuration. We have liquid phase leaving the system. And now we have a gas distributor with which I contact a gas by bubbling it through and then I take the gas out. Okay, this is how they make carbonated beverages. That they bubble carbon dioxide through the liquid beverage until the solution is saturated. There you have your soda pop. Now, because of the hydrostatic head, the bubbles at the bottom, let me refrain from a solid bubble. The bubbles at the bottom will have a size due to the hydrostatic pressure. If nothing happens, as they move up through the buoyant forces, they should start getting bigger and bigger. right? As they move up, their size should increase because the hydrostatic pressure decreases as we move up. However, now our bubbles transfer its load to the liquid side. So we have a transfer to the liquid side. And the content is decreasing. And therefore, the size of this bubble is not going to be estimated simply from the hydrostatic pressure. And of course, as the hydrostatic pressure changes, the pressure inside this bubble changes. And here we have a gas-liquid interface. Now it is that reactor, batch reactor that we envisioned in the earlier lectures, perfect batch reactor. Now let me close up to the bubble. But now it is filled with a gas. But now I don't have any forced flows of liquid in and out, but my molecules diffuse through the boundary. How do they diffuse? By the same mechanism as we have discussed a moment ago. So when I, again, get a close-up perspective of a very small portion of the surface of this bubble, I have an interface. Here, this interface is the boundary between the liquid and the gas. This is my flat interface, close to be flat interface. On this side, I have gas, and gas molecules. They move so rapidly that we can take the concentration on the gas side uniform. All right, so let's call this T infinity. It's going to uniform across the interface. But when we have a liquid which is being stirred by an impeller around this gas bubble, we will have some domain that is not going to behave like bulk, but beyond that we will have C infinity liquid. And here we have the boundary layer within the liquid domain. Again, from the two-film theory, constant molar flux gives us a flat concentration profile. So here, this flat concentration profile overlooked the fact that between the gas and the liquid, there might be an interfacial concentration difference that is dictated by the thermodynamics. In other words, we overlooked the Henry's law. If we take care of the Henry's law, this problem, we're going to have a gas concentration which is uniform. With that gas concentration, we are going to have an interface concentration, and the interface concentration and the gas phase concentration are related to one another through Henry's law. or through absorption, desorption thermodynamics. At this interface, we have a film mass transfer. Beyond this, we have the bulk liquid concentration. So this is how we make carbonated beverages. Now, we are not considering any reactions so far. We are not considering any reactions so far. When we start considering the reactions, we have to take that reaction into consideration also at the interface. Now, in that mixed flow reactor, we might have solid catalysts, which I'm going to add to our figure as filled circles. Now, those solid catalysts change the game, and this game that we're going to play now is going to be a gas-liquid-solid type of reaction, where we are going to gas, liquid, solid type of a reaction, where we are going to have our solid sphere, the catalyst. This is solid. The solid is surrounded by a liquid film. All right. So here we have our liquid film, which we might just take that liquid film moves with the velocity of the solid particle. As far as solid particle is concerned, that fluid film is stationary, and that liquid film is stationary. And somewhere up here, we have a gas bubble, a gas molecule diffuse through the liquid by molecular motion, penetrates through the liquid film, penetrates through the solid catalyst, goes through a reaction, and let me call this reactant A, and the product has to move through the solid, move through the liquid boundary, and then go back to the bulk liquid as B. And these type of reactions are not uncommon in chemical process industry. The solid catalyst in this multiphase medium of gas, liquid, solid domain is a porous material. It has to be porous because we need to make sure that we have maximum available number of active sites, and the only way that we can ensure this is to have a porous structure onto which we load the catalysts. Now, the porosity in that catalyst I represented through the tortuous paths, the lines. Now we are going to start our discussion from this spherical geometry with a tortuous geometry within itself. Now let's just get close-up pictures. Now first I will look at the catalyst domain by cutting a slice on the outer edge of this catalyst. We are going to have macropores. These are macropores. Macroscopic pores that are interconnected to one another. All right? They are of irregular shape, and the molecule, when enters, it can have a tortuous path when traveling through this domain. So we have macropores. Of that macropores, when we get a close-up, let's get a close-up of this macropore. Let's expand this. So we have this macropore like this, through which we have micropores. Right? And those micropores, relative to those macropores, may or may not be dysregular, but remember, as we expand our view, we are getting closer and closer to the atomic molecular sizes. And those micropores, let's get a close-up. We have active sites. These are active sites. Those active sites could be the sites, the surface sites of that micropore itself, or we might deliberately introduce active catalytic material onto this porous structure, such as a precious metal, like platinum, for example, and the active sites are the sites over that platinum. Now let's get a close-up if that's a platinum particle. That platinum particle is of the nanometer size, and it's most of the time of the cubo-octahedra shape. Right, and the active sites, as we close up to the surface, are the platinum atoms. And the orientation of those atoms change with respect to the position of the atom, whether it is on a flat surface, 0, 0, 1, or a diagonal surface, 1, 1, 1, or is it located at the edge or corner of that particle. Now we are going to ride with a molecule. Let's be a gas molecule that entered into this reactor. First went through the gas distributor. It was in a gas bubble, flying in a gas bubble. Now this gas bubble, the bubble, is serving as the vehicle that we transport this gas molecule. We're just looking at one molecule. That molecule, feeling the chemical potential difference between the gas domain and the liquid domain, diffused out of the gas bubble into the liquid domain. Now this gas molecule is a dissolved gas molecule in the liquid phase. All right? This gas molecule in the bubble felt the chemical potential difference, moved into the gas domain, is transported through the liquid film, and it is now a dissolved gas in the liquid domain. That liquid domain carried this gas molecule until this gas molecule is close to a catalyst particle. When the gas molecule arrived near a catalyst particle, and this catalyst particle is also surrounded with that liquid, of course, and the pores of this solid particle is filled with the liquid, this gas molecule is now moving through the liquid that is filling this solid particle. The liquid that is filling the solid particle is no longer the bulk liquid. It is the liquid and the solid. It is subject to different constraints and conditions. And some of the liquid is really a stagnant liquid. Okay? And this gas molecule is moving through this stagnant liquid, bouncing off the walls until it arrives at an active site. On this active site, it changes its nature. It was A, now it become B. Now this B molecule is going to sense the chemical potential difference, that B is more depleted outside. And it will just take the reverse path and travel outside. And eventually, we will take our gas, we will take our liquid. Both of them have undergone chemical conversions. And now we will learn the tools and techniques that will give us the behavior of this gas molecule on a macroscopic sense through the system. Our objective is to be able to design, to be able to estimate how much gas should I send in, how much liquid should I send in, what should be our catalyst particle size, what should be the pore size of our catalyst, and so on and so forth. All right? So far we were designing the reactors with respect to their volumes. Now we have to take a lot of other things into consideration. We have to design the gas distribution systems so that it will give us sufficient size of the gas bubbles that will survive through a hydrostatic pressure in order to be able to give us sufficient A molecule after this tortuous path at the active site. Now we are going to discuss how effective our catalyst is. Concept of effectiveness factor. Remember, this is a conceptual discussion. We are going to derive the equations afterwards. Now, the tortuous path that the gas molecule A has taken, starting from the gas distribution plate, all the way through the pores of the macroscopic and microscopic pores of this catalyst, arrived at the active site, it took some time. So, if that time is not significant relative to the time that this whole fluid domain traverses through our reactor, liquid and gas, we have a very effective catalyst. But if that time is longer, that it takes longer for that molecule to arrive at the active site, then our characteristic residence times, we have a problem. All right? That we don't have an effective catalyst. So the effectiveness factor is the definition, is a dimensionless quantity. We frequently denote it by Greek alphabet letter eta. This is a number. In the best situation, it is going to be 1. So we are going to have reaction rate evaluated at the active site. All right. Divided by the reaction rate evaluated at Ca bulk. So if my molecule can rapidly reach to the active site so fast that it is always at the bulk concentration. My effectiveness factor is 1. Effectiveness factor is a quantity that changes between 1 and 0 for isothermal conditions. So, the effectiveness factor depends very strongly on how well our molecule travels through the solid. Okay? The bulk and surface definitions in some conventions are different, but with this bulk we are talking about bulk of fluid. This is the active site. Okay? So say that we are dealing with a pseudo first order reaction. Rate is equal to K times Ca. When we are estimating the effectiveness factor, we evaluate this K times Ca at the site. Let me be precise here. Divided by K times Ca, the bulk fluid. Okay, for first order reactions, K's cancel and the effectiveness factor is the simple ratio of the concentrations at the site and in the bulk. So if we can devise a model that gives us this concentration ratio, then we know how effective is our catalyst. So if we know how effective our catalyst is, then all we need is the bulk concentration. We can have the value of the effectiveness factor, and we can estimate the rate in the bulk as the effectiveness factor times K times Ca bulk. We don't have to know the concentration at the active site. We don't have to know the happenings through the transport and on the surface. With a correction factor, we can simplify this complex physical process into a homogeneous, but this time it's pseudo-homogeneous, problem with a correction factor of the rate constant. Then we can just take this reactor and model as a CSTR and size it. And of course, we have to verify what we have done is accurate. So now let's see how our reaction is going to take place if our catalyst is modeled as an infinite slab. Infinite slab was the close-up version of our spherical catalyst. If we zoomed in close enough to a perspective, the outer boundary layer can be approximated as a two-dimensional surface, and infinite slab, infinitely ranging in the x and y direction, and we have a finite thickness of delta in the z direction. So we are writing the species conservation equation in a z direction, and this is the new term that introduced itself after we started discussing the issues around interface. Those two terms are our good old balance terms. This was the advective transport term, how Ca is transported in the z direction. This is our rate. And this is the diffusive transport term that now made itself into our equation, because we have to take that diffusive motion of the molecule through our system. Our system is the layer of the catalyst that behaves like an infinite slab. Now, our discussions so far brought us to the understanding that if the concentration in the bulk is close to the concentration at the active site in the bulk of the catalyst, that our effectiveness factor is 1, that diffusion is rapid. We can even disregard it in this equation. Okay? And the reaction is homogeneous. That our rate appears in our balance equation. But if the reaction is so fast that the moment that our molecule touches the surface of the slab, the reaction takes place and our reactant disappears, our rate has to appear only at the boundary condition. It shouldn't be present here because this balance equation represents the phenomena taking place within those two slab boundaries. So here we have Ca bulk, here we have Ca bulk, that molecules are diffusing through the center, reacting in the center, and B molecules are diffusing out away from the center. So if we have, again, one more time, if our reaction is slow, our rate expression appears in the balance equation. If our reaction is very fast, our rate is going to appear at the boundary condition. That would be the condition representing heterogeneity. Now, let us say that our reaction rate and the rate of diffusion are comparable as well as the advective flow. All right? So those three components are present in our balances, and we're going to have some boundary conditions. This is the slab at Z is equal to, so Z starts from here, so we have delta, plus minus delta, we have Ca to be equal to Ca bulk. Now, with that, we provided two boundary conditions. But there's an additional boundary condition that you can also use. Sometimes that is more useful. That is the symmetry condition. It is dCA over dZ at Z is equal to 0 is equal to 0. That is the symmetry condition. That concentration is symmetric across this geometry. Now, solution of this differential equation is going to bring us any parameter which is called the Thiele modulus. All right, or Thiele parameter. This Thiele modulus is going to scale the rate of reaction with respect to the rate of diffusion. I'm not going to go through the solution of this equation, but I'm going to discuss the end result. The solution is an exercise, both generating an analytical solution or generating a numerical solution is going to be our exercise, which we'll be performing on a different platform. But I'm going to discuss the implications of this problem. Here my plot is going to be the effectiveness factor versus the Thiele modulus. All right. So let's first derive the Thiele modulus and then get a qualitative plot. I will rearrange this differential equation. dA d square Ca over dz square minus Vz dCa over dz plus R sub A. R sub A was minus k times Ca everything is equal to 0. For a first order reaction, of course, it's not general. For first order reaction, R sub A is minus k times Ca. Now we're going to make this equation dimensionless. First, let's make our z dimension dimensionless. Let us generate a new dimension coordinate called theta, which is equal to z over delta. Delta is the thickness, all right, not the full thickness, half thickness. So dz is going to be equal to delta times d theta. And substituting that into this equation, we are going to get dA times delta square times d square Ca over d theta square minus Vz times delta dCa over dz minus k times Ca to be equal to 0. I'm not going to play with making Ca dimensionless. It's going to be more convenient if you have your Ca dimensionless, but let's not deal with it right now. Let us have our first term to remain independent of any multipliers. In order to do that, we're going to divide the whole equation by dA times delta square. We have d square Ca over d theta square minus Vz over dA times delta times dCa over dt, dCa over d theta. This is also theta. Minus k over dA delta square times Ca to be equal to 0. Now let us take this quantity and let's see what kind of dimension does it have. Vz divided by diffusivity dA times delta square. I'm going to do a dimensional analysis. Vz, linear velocity, length per time. Let's say time. There's no temperature here. I can use T for time. dA, length square, length square times divided by time times length square. I'm sorry, this is not, sorry about that. This is length over time, length square over time. There's something not quite right here. All right, of course, this is going to be in the denominator, my mistake. This is going to be in the denominator. So this is going to be in the denominator. We are going to clean this up. Okay? So VZ delta, when we make mistakes, we just take the responsibility and correct it. Delta is here, this is length. So we have length square over time divided by length square over time. There's no dimension. Those length square over times canceled one another. All right? So here, this term is the reciprocal of the characteristic time for advection. This is the characteristic time for diffusion. Now let us examine this term. Of course, we have to clean that up and make it accurate. So we're going to do the dimensional analysis here. We're going to have K times delta square over dA. This is rate constant, first order rate constant. It is 1 over time. Delta square is length square. Diffusivity, length square per time. And they canceled one another. Now we have two terms here. This should be familiar from our earlier discussions. Now this group is giving us a reciprocal time here. I'm going to represent it by 1 over K. And I'm going to call this characteristic time for reaction. There is another group here. I'm going to take this. Okay. Delta square over dA. And this is characteristic time for reaction, for diffusion. Now when we compare the characteristic time for reaction to the characteristic time for diffusion, we will know which one is dominant. All right? So this group, K delta square over dA, let me call this characteristic time for reaction as tau sub R for reaction. Let me call this as tau sub D, characteristic time for diffusion. And this group is tau sub D over tau sub R. All right? How fast my molecule is diffusing? How fast the molecule is reacting. Now, when D is 0, characteristic time for diffusion becomes infinite. It takes infinitely long for the molecule to arrive at the site. But when D is infinite, when it is infinitely large, that characteristic time for diffusion becomes 0. That the molecule diffuses immediately. When the molecule diffuses immediately, my catalyst is very effective, my effectiveness factor is 1. Right? So it goes through a behavior like this, and it falls off. And this graph is logarithmic. All right? And this characteristic time for diffusion, the characteristic time for reaction, raised to the power 1 over 2 is the Thiele modulus. Now what happens if we increase the temperature? Or if we change the temperature? Remember that in these reactors, endothermic or exothermic reactions are taking place. In other words, as a result of reaction, there is a heat generated or absorbed from the environment. And we are more concerned about heat generation. I will tell you why in a moment. Because heat generation is going to cause a change in the surface temperature, catalyst surface temperature. If the catalyst surface temperature changes, the temperature dependency of the rate constant is going to start to play a role in how fast the reaction is moving. So if we cannot remove the heat as fast as it is generated in such systems, and if our reaction is very rapid, we cannot do that very effectively, then our rate constant increases. So this effectiveness factor behaving between 0 and 1 is valid only for isothermal situations. Effectiveness factor decreases with temperature, of course, or if the temperature decreases. But when we have problems of heat transfer in the catalyst domain, we might have situations that give very strange results, that our effectiveness factor exhibit multiplicities, that we have multiple values of effectiveness factors for the same Thiele parameter, 1, 2, 3. So the multiplicity of these effectiveness factors are due to different zones of temperature in the catalyst particle. Outside the surface, the temperature is equilibrated, the system is thermally equilibrated with the environment. In the middle of the catalyst, we have very high temperatures, all right, and then we have strange behaviors of effectiveness factors increasing with decreasing Thiele parameter. These domains are domains of instability, but we have some meaningful behaviors of effectiveness factor as a function of Thiele parameters. But these are the non-isothermal effectiveness factor behavior. You must be aware of the fact that this scale is logarithmic, and this non-isothermal effectiveness factors can go as high as 1,000. In other words, our reaction rates could be 1,000 times faster, that our temperatures may increase 1,000 times faster than the isothermal situation, and that might lead to disruptions in the catalyst or in the reactor. This is something that we have to evaluate, not by only solving the species conservation equation, but also we have to solve energy balance along with it.